So last class, we sort of looked at what is a neural network, or particularly what is a neuron, and how one can use that to classify data points that are separated by a hyperplane, right? So, and then we also saw how to combine them so that we can get a classifier that is more complicated than a simple linear classifier. Okay, so we just looked at, this is a big picture of what neural network is. And the second thing that we started looking at was, if you want to come up with an algorithm that will return a neural network weights, which optimizes some loss function, then you have to have an algorithm, right? So basically a gradient descent sort of algorithm. So that means the algorithm, what it does is at each time it will give an updated neural network weights, right? So eventually, if you want to implement it, you should basically give certain guarantees, right, for the algorithm. If the algorithm will never settle, right, so it will keep on oscillating, then you will never know when to stop. And moreover, even if let's say the neural network weights sort of seem to converge to a point, then you should also talk about what is the performance and so on, right? So towards that, we started looking at the notion of convergence. So that's what we did in the last class towards the end, right? So what is the definition of a convergence? So when do you say that a sequence AN converges to A? Epsilon room definition, right? So you take a point A and then take an epsilon room around it, then the sequence beyond certain stage will enter that room and will stay there forever, right? If you if you reduce the size of the room epsilon, then still you can ensure that the sequence will enter that room, but perhaps at a later stage, right? So in other words, for every epsilon greater than 0, there exists a stage which is n epsilon, such that for every n greater than n epsilon, an minus a, this is the epsilon room, right? So this is the definition of convergence. Is that clear? Any questions or intuition clear about this? Okay, so maybe we'll just look at one simple proof of convergence. Suppose, let's say you have two sequences. Let's say, okay, so problem. If let's say an converges to A and Bn converges to B, implies An plus Bn converges to A plus B. So how do you prove this? It's very intuitive, but how do you prove this? So I know that An converges to A. So what does that mean? There is an epsilon room around A, so that the sequence An will enter that room, right? So there exists so let's fix an epsilon. So give any epsilon, right? Any epsilon greater than 0. Okay, you fix this. Now for this epsilon, I can find a epsilon, the stage beyond which this will enter this room, right? So An will enter this room. So there exists, let me call n epsilon by 2 of 1. So instead of taking an epsilon room, I'll take epsilon by 2 room. Okay, we'll see why that is the case. So such that for every n greater than or equal to n epsilon by 2, 1, what will happen? An minus A will be within epsilon by 2, not epsilon, right? So this is the first thing, right? So what is the second thing that you can expect? So similarly, for Bn, there is a stage, let me call this as n epsilon by 2, such that you take any n, that is a sequence beyond this stage, that is greater than or equal to n epsilon by 2 of 2, Bn minus B will be less than epsilon by 2, right? Beyond that, it will enter that room. Now, what is it that I have to prove? An plus Bn, which is a new sequence, let's say Cn enters an epsilon room around A plus B for sufficiently large n, right? That's what we need to prove. Okay, so need to prove that An plus Bn, this is Cn, minus A minus B, this is A plus B is your C, is less than epsilon for any n greater than or equal to some n epsilon. Okay, this is what we need to prove, and this should be true for any epsilon, right? So by the way, this whole statement that I have written here is true for any epsilon greater than 0, right? So now let's see how do you prove this particular thing here, right? So how do you prove this quantity? Now, instead of proving that this is less than epsilon, an plus b1, bn minus a minus b less than epsilon, I'll prove something larger than that less than epsilon. That's good enough, right? So let's consider this difference. an plus bn minus a minus b, I'll write it as an minus a plus bn minus b. Now, what do you think is the next step? Can you see direction here, how to go about proving this? Can somebody tell me? Triangular inequality, right? So what is that? an minus a plus bn minus b, right? But this is less than or equal to what? Epsilon by 2. I'll write it here. For all n greater than or equal to n epsilon by 2 of 1, right? Similarly, this will be epsilon by 2 for all n greater than or equal to n epsilon by 2, 2, right? Well, both will happen provided n is sufficiently large. It should be larger than the maximum of these two, right? If n is, let's say n epsilon by 2 of one is 100, the other one is 150, then you take capital N epsilon to be 150, then it will be always true, right? So this is greater than less than epsilon for every n greater than or equal to max of n epsilon by 2 of 1 comma n epsilon by 2 of 2, right? Is this clear? So that's QED, right? So you're done. Okay. So was there a question? Yes, Saurabh.
Sir, how can we guarantee that both an minus a modulus will be epsilon by 2 and bn minus b modulus will be epsilon by 2? I mean, both the same quantity, how can we define? It should be one epsilon 1 and one will be epsilon 2.
No, so you give me an epsilon, I can guarantee that, right?
So, but both becoming same quantity in this case.
So you give me any error, epsilon, an will enter an epsilon room, right? That is guaranteed. So bn will also enter epsilon room around b. That is guaranteed by convergence of an to a and bn to b, right? So that will guarantee that you can always, so you should be able to enter. So supposing, let's say you travel from here to Bangalore, what does that mean? You converge to Bangalore, right? What does that mean? That means you should enter a 50-kilometer radius around Bangalore, right? And stay there forever. Otherwise, there's no guarantee that you will reach Bangalore, right?
Yes,
and stay there forever, right? So, you can shrink that 50, you can make it 30 and so on. So it doesn't matter. Is that clear?
Yes, sir.
Okay. Okay, so is this proof clear? Well, all the proofs will be along these lines. So you should think geometrically and convert the geometry into Greek and Latin, right? So this is in fact a very, very rigorous proof. Even if you go to any math class anywhere in the world, this is how the proofs are presented. Okay. Okay, so let's move on. So the other thing that we started looking at in the last class was what? Interval, right? What is an interval? Very easy, right? So we looked at various intervals like this: a comma b, closed on one side, open on the other side, both closed. These are the possible intervals that you can have, right? The difference is basically you will just not include one of the points, that's all. So then we looked at what is known as an open set. What is an open set? Can somebody tell me? When do you say that a set is open? You take a point, you take a point in the set, then you should be able to accommodate a small interval around it, right? If you can do that for every point in the set, we say that it's an open set. So for example, let's say 2 comma 3 union 100 comma 101. Okay, this is an open set, right? Well, this is not an interval. Why? It's union of intervals, right? Union of intervals can never be interval. Okay, so how do you mathematically define this open interval? You say that You take any point X in the set, there exists an epsilon room around it such that the entire epsilon room belongs to that set, right? That's how we defined an open set. Okay, so at least intuitively you got to know what is an open set, right? Clear? Okay, so these are some of the jargons you might need, but in practice, for example, if you want to implement a neural network or some you want to achieve some data analysis task, then you may not need to know what is an open set very rigorously. Okay, so what is a closed set? This is something that what is a closed set? If its complement is open, okay, so a set, you take a set, okay, so let me call this C, which is a subset of R, is set to be closed, if C complement is open, right? What is suppose okay, let me look at the example here. So suppose I have 2, 3, and this is a closed set. Do you agree? Why? Well, let's look at the complement. What is the complement of this? All the numbers between 2 and 3, 2 and 3 included, should not be there in the set. So what do you mean by that? You start at -infinity all the way till 2, 2 not included, right? Union all the way from 3 to 3 not included to infinity. So this will be, so this is an open set. Why? You take any point in the complement, right? So I can always find an epsilon room in the set. Okay, is this fine? It's like this. If I want to call this room as an open set, then the wall should not be a part of this, or the edges should not be a part of this particular set. Then you take any point inside this room, then I can find a small tiny room around that, so that the entire that tiny room is within this room, right? That's what it means. Okay, is this clear? Okay, one more notion. Okay, so this is something that you will see in the subsequent lectures later on. A compact set. How many of you have heard of a compact set? Yes. Have you studied this in your calculus course? Compact set? Huh? Well, nothing great. It's a closed and bounded set is a compact set. Okay, so a set is set S, or is compact if it is closed and bounded. Well, what do you mean by bounded? Can somebody tell me what is bounded?
It has fixed points where it ends.
Well, it's very vague, right? Yeah, you are right. I mean, pictorially, that's what you see. You should end somewhere, but you should be a little more precise, right, when you say that. So
converge at a point.
Okay, so 1 second. Let me ask people here. Yeah, you were saying something. Oh, there is no series. It's a set, right? Okay, so essentially you take any point in the set, mod of that should be less than infinity, right? That means x should be less than infinity, or x should be greater than -infinity, right? Strictly greater than, then it's bounded. So in other words, you can put that set within a larger but finite size set, right? Then we say that it's bounded. Okay, so let me write it here. So what is a bounded set? A set is bounded if for every x in the set, a set let me call B, okay, B is bounded if for every B mod x is less than infinity. Okay, it's a bounded set. What is a closed set? You know what a closed set is, right? The complement should be open. So can you give me an example of a compact set? Huh? Concentric circles. Let's only stay in R now. Okay, let's not go to R2 or higher dimension. In R, can you give me an example for a compact set? Huh? But the definition says it should be closed, right? You cannot take an open set. All open sets are excluded now. You cannot say that the moment you say open, then it's not a compact set. Closed set 1 to 2, right? So example, closed set 1 to 2. Anything else? You see why it's called compact, right? It's like one go and it's very compact, right? When you say it's not compact, you have some chunk here and you have some other chunk here and so on, right? So, I mean, there is lack of. So, what about? Okay, let me ask you this. What about this guy? Is it compact? Yes, right? Why it's closed? It's bounded because all the numbers are finite, right? Right. So there are so many examples of compact set. Okay, so keep this in mind. So why is it important? Well, it turns out that if you have a function, let's say a nice continuous function. So we will see what continuous functions are. Yes. It's closed but not compact. Okay, so this is a trivial example, right? It's not closed, it's closed but compact, not compact, right? Or I'll include infinity as well, right? It's closed but not compact. Okay, so fine. Okay, so if you take a continuous function in a smaller, let's say over a compact set, you can always find a minimum. Okay. So that's why compact sets are very important, because the moment you say a function over a compact set, then you are guaranteed to find a minimum, right? Whenever the function is continuous, right? At least you are guaranteed, right? Therefore, compact sets are quite important. Okay. So now there are two other very, very important notions which I will talk about, and then we will move on to maybe linear algebra. Okay. So suppose I take this again. This is an example. Suppose I give you this set, okay? So 0, 3. This is a set, right? Can you give me the maximum element of the set? What do you think is the maximum element? See, by the end of the day, you have to find maxima, minima of something, right? So let's start with the set. So what is the maximum element of this set? Okay, what is the maximum element of this set? 3, right? What about 0, 3, where 3 is not included? What is maximum?
2, sir.
Yes.
2, sir.
How can 2.1 is more than 2, right? So that cannot be maximum, right?
The limiting value that is going towards.
That is going towards is not the answer. You should give me one number, right? So whenever I say maximum, you should say one number, right? Right? So, doesn't exist, right? Maximum doesn't exist for this, right? This. But what can you say about 3? You know, if you are a practitioner, you can afford to, you know, pull 3 into the set and say, well, 3 is a good number, or something very, very, very close to 3 is a good approximation for maxima, right? So now we will have a name for this. So for example, 3, although not a maximum number, strictly speaking, why? Because 3 is not there in the set, right? So therefore I cannot say 3 is maximum. We'll give it a name. So do you know the name for that? Supremum, right? How many of you are familiar with this? All of you are familiar? Okay. So this is called the supremum. Okay, supremum of the set. What can you say about minimum element here? Now, what is the minimum element of 0, 3? This particular set here? 0, right? So that's the minimum element. What about this set? What is the minimum? Doesn't exist, right? What about infimum? 0. So how do you define infimum and supremum now? Well, how do you define? Well, let's look at number. Let's take some hint on this. So let's say 0, 3. Well, if I take a number here, for example, 4, what can you say about this number? Definitely 4 is larger than every element in the set. So it's called an upper bound, right? How do you define an upper bound of a set? Well, a number A is said to be an upper bound on the set capital A. If you take any element in capital A, it's smaller than small a, right? So that's how you define upper bound. Now, what can you say about this? Let's say 3.5.
Lowest upper bound.
Yeah, lowest or the least upper bound is called a supremum, right? So least upper bound of a set is called the supremum. Okay, so you can mathematically define it. I think I just now mentioned how to define mathematically. What about infimum? So let's say -1. Do you think what can you say about -1? So any element in the set 0, 3 is larger than -1, right? What about -0.5? Still larger, right? All the elements. So now, how do you define infimum? Huh? It's the greatest lower bound, right? So, okay, so I'll write it here in different color. Lower. So it will be infimum. Okay, simple. And it should be not least, right? Greatest. Greatest lower bound is the infimum. Okay, now let's look at one example. 0 to 3 union 5 to 7. Now, can you tell me what is the infimum of this? What is the infimum? 0. What is the supremum? 7. What is the minimum? 0. What is the maximum? 7, right? So infimum, supremum will coincide with max and min, right? Min and max, right? So whenever it does not, so infimum, supremum always exists. So therefore, in optimization, we end up doing a lot of optimization in this course. So that means max over all x f of x. So I want to maximize a function. Well, what is the guarantee that the maximum exists? We don't know. So to be on the safer side, we'll just say supremum. Okay. Instead of saying minimize, to be on the safer side, we'll always say infimum. Okay. Then we need not worry about whether it exists or it will always exist, right? And for practical purposes anyway, the infimum will be very good approximation for the minimum also, right? Whatever, practical minimum, right? Okay, so let me ask you one interesting question. So suppose I have a set which is just 0, one singleton. What is the supremum and what is the infimum? Huh? What is the supremum? Okay.
0.
Huh? 0, right? What is the infimum?
0.
So infimum, supremum will coincide. Suppose I take a null set. You know what a null set is, right? This is a slightly aside, but it's interesting. So what can you say about the supremum of this set? Huh?
Should not exist.
No, you cannot say that. No. Okay, let's go back. So suppose I have 0, 1. How do you find the supremum here? One way is, practical way, but very crude way, is you start some piston at infinity, let it move to the left. The moment it hit the set, you stop there and see what is the point. That's the supremum, right? Similarly, you start a piston at minus infinity and see where it stops. That's the infimum. So for 0, it will stop exactly at 0, right? Both the piston will come and stop, right? So 0 is the infimum and supremum. But what about null set? Huh?
Every
So
number is a.
this will go here and this will go here, right? I mean, there is nothing to stop. So the supremum of a null set is infinity and the infimum is minus infinity. And that's the only set where supremum is smaller than the infimum. Okay, you can mathematically, argue, right? So what is the supremum? Least upper bound, right? So any number, least upper bound, okay? So any number is an upper bound for null set because there is nothing there, right? By definition. So, well, crudely speaking, there is nothing there, right? So you keep on taking numbers and go on, reducing the number, it will go to minus infinity, and similarly for infimum. Okay, this is just a fun stuff. Okay, so now one very, very important thing. So you know what a function is, right? It's a mapping, right? So when do you say that a function is continuous? Can somebody tell me how do you define continuity of a function? First, let's take a point and then see what is the continuity of a function. So let f be a function. This is how we write, right? Mathematically, it takes a number and gives another number, right? So it's a mapping from R to R. Be a function. Okay, now I want to talk about continuity of this function at some point x naught. So how do you define continuity? So let's look at this function. So for example, this function looks like this, let's say, right? And you have taken a point, let's say x naught here. I want to see whether it is continuous or not. Don't tell me that you can write this function without lifting the pen and all that. Well, maybe from a practical standpoint, yes, but you know, what is the proper definition of a continuous function? Huh? Check the limits. Limit of what? No, I know how to take the limit of a sequence, right? I know convergence of a sequence, but I don't know what is the limit of a function, right? What can you say about this? So now what I can do is I can suppose x naught is a see, I know how to I know how what is a sequence and how what do you mean by convergence of a sequence. Now I have to somehow convert this whole notion into a sequence, right? What do I do? What do you mean by limit of left and right? Oh, okay. So in the interest of time, maybe I'll okay, maybe I think I should let you speak. Yeah. Okay. So essentially, you know, you take any sequence xn that converges to x. Okay. Take any sequence xn converging to x naught. Well, xn is in R, so we don't have to worry about whether f of xn is defined or not. So it's entire R. That's how I'm defining. You take any xn that converges to x. Okay. If f of xn, so what can you say about f of xn? F of xn, x1 is a number, f of x2 is a number, f of x3 is a number. So it's a sequence, right? Now, if f of xn converges to f of x naught, right? So no matter what sequence xn you take that converges to x naught, we say that the sequence, the function is continuous at x naught. Okay. Can you write the definition of the continuity of a function? So definition, I'll leave it. Okay. Continuity at x naught. But what do you mean by continuous function? This is only continuity at x naught. But if it is continuous at every point, right, then we say that it's a continuous function, right? So one more small jargon. So the thing that get mapped to is called domain of a function. Okay, this is another jargon. This is called range. You know that, right? It's very clear. If maps to something, that's the range, right? This is the domain. Okay, this is just another name. Everything clear? Okay. So now, okay. So what is the next step? Suppose example, not example, it's problems. So if you take two functions, okay, f and g. Well, I won't write f of x, g of x. Okay, f and g means f of x and g of x, or two functions, two continuous functions. Then what can you say about f plus g? If two functions are continuous, intuitively, you know, the sum also you should be able to write without lifting the pen, right? So intuitively it is a continuous function. Some alpha f, that is, you take f of x, you take 100 f of x, 100 times f of x. That's also a continuous function, right? F by g, is this a continuous function? Huh? Is continuous if g is not equal to 0 for all x, right? If, okay, let me write this as a condition. G of x not equal to 0 for every x. Okay. What else? What about f times g? It is, right? Product of two functions. Okay. So, well, this would be an exercise, but how do you prove the product? Suppose you have proved everything else. How do you prove product? Okay, one more thing I'm going to add here. Okay, so maybe I'll add it here. Let me call this as 1 dash. F squared, what can you say about F squared? If F is continuous, F squared is also continuous. Now, can you put everything together and prove that F times G is continuous? See, first thing says F plus G is continuous, right? The second thing says that if a function is continuous, square is continuous. Can you complete the proof now?
Yes,
If F is G is continuous, minus G is also continuous because alpha G, right? So now F minus G is continuous, whole squared is continuous. What should I do? I should add, then again alpha, right? Right? Easy proof. That's why I completed the proof for this, but the remaining it requires a little more effort. Okay, but you should remember this anyway. This will be part of your homework problems. You will try to prove some of these. Okay, fine. Okay. Okay, so this is the math, slightly more rigorous math background that you need. Whatever the rest of the things will be more geometrical and intuitive. Okay, so let's start by looking at linear algebra because, of course, when we look at convergences, it's not convergence of sequence of numbers. We should also talk about convergence of sequence of vectors or some neural network coefficients, which is of size 1 million by 1 or 10 million by 1, right? A huge vector. What do you mean by that vector converging to something, right? So in order to understand those, we need to know the notion of vectors, we need to know the notion of matrices and so on, right? So let me start with one interesting problem in data analysis or machine learning, which will sort of motivate us to study more about linear algebra or matrices. Okay, so this problem is about making the problem simpler in data analysis. Okay, so we saw this problem of classification, right? So you have some, so I'm assuming that you know some notion of higher dimension, right? So you take some 100 numbers together and write it as, you can think of it as a vector, right? So you have, let's say, so many points in higher dimension, and there are the other points, let's say non-spam, again 10,000 dimension vector. I have all these points, right? But typically I don't want to work in 10,000 dimension space. Why? Because computation wise, you have 10,000 numbers to deal with, right? So I want to bring this down. Suppose I want to share this data online, right? So I don't want all the 10,000 numbers to be there. Each component here is like 10,000 numbers. Now what do you do? How do you reduce? Maybe you can knock off a few entries, right? That's one way. You may think that certain words will never appear, maybe we'll throw away those numbers, but there is no systematic way of throwing numbers, right? And what else? So even if you do that, right, so what will happen? Suppose I have, let's say in 2 dimension, let's say x comma y. If you drop off y, you will get this point x, right, in lower dimension, this one number, right? Similarly, if you knock off a few numbers in these components in these vectors, then it will go to a lower dimension. What might happen is you have spam here on one side, non-spam on the other side. When you pull it down to a lower dimension, it can mix up, right? The moment it mixes up, there is no way by which you can say that, okay, something is spam and something is non-spam. Do you agree? For example, if you project, let's say, I'll also, just for the sake of, I'll write like this. Now, if you project, what will happen? All these points will be, let's say, I'm going to project to x-axis. All these points will be here, right? All the other points, right? For example, these points will also come and sit here, right? So everything is mixed up. So if you just look at these data points, you will never be able to say that, one is spam and one is non-spam. So there is no point in reducing the data points here, right? Because you can't solve the original problem. What is it that you have to do? You have to project, or you have to bring it down to a lower dimensional space, but in such a way that these two are separated, right? Is that clear? So how do you do that? Well, you take a vector, let's say 10,000 dimension, you reduce it to 1,000. But if you take the 1,000 dimensional vector corresponding to spam, 1,000 dimensional vector corresponding to non-spam, and look at the distance between them. Well, what do you mean by distance of two vectors, right? That's another question. How do you measure distance? How do you measure distance in 10,000 dimension space or 1,000 dimension space? Any idea? Huh? How do you measure distance between two vectors? Huh? That's a similarity, right? Not the distance. Huh? Norm of the? Okay, so what norm we will pick? Okay, so that's called Euclidean norm, the usual distance, right? There are several other ways by which you can measure the distance, which will be quite useful in data analysis. Okay, so not just the Euclidean distance, some other distance will also be useful. Okay, so in general, you need to know how do you define distance between two vectors, how do you project these vectors, right? This is a very practical problem. Do you agree? I mean, it's not some very abstract problem that nobody wants to solve, right? Only you solve it for fun, right? So this is very useful and it's also fun, right? So you need to see how you bring down the data points to lower dimensional. So this sort of motivates us to study vectors and what do you mean, what are the properties and how do you, what do you mean by projecting or bringing down the dimension and so on, right? And what do you mean by dimension, right? Some of these things we'll quickly go through. So I think you might have taken, you have taken linear algebra, right? So what all have you studied there? Maybe depending on that, I'll modulate whatever I wanted to say. Yes. Can somebody tell me? Can somebody tell me online people? Not many actually, only 17. Huh? Yes.
Hello, sir.
Yes.
Sir, basically in linear algebra, we have studied about the simple systems, I mean systems of a solution till now, and how to diagonalize it. So, and what are the requirements for that?
You are a grad student or no, right?
No, sir.
Okay, good. Okay, it's Saurav, is it? Okay. Okay, so okay, so now let's look at anyway. It will be a recap. So, how many of you know what determinant is? What does it signify? You know how to compute determinant, right? How do you compute determinant? Well, one way is you take this element and look at the determinant of this, that you take this element, and if it is 2 cross 2, then you multiply and subtract, and very complicated. And if you look at the formula, it will be summation over all permutation minus 1 power blah, 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 right? So very complicated beast, right? So, but what is the intuition? I mean, what does it give us? Any idea? What is determinant?
So the area that it gives us.
Area of what?
Area of four-sided figure, so parallelogram or something.
Okay, so this is what it is, right? So for example, I take 1, 2, 3, 4. Okay, this is my matrix, right? What is determinant? 1 times 4, 3 times 6, right? So it corresponds to you can think of each of these as vectors, right? You have one vector like this and the other vector as like this. You form a parallelogram. The area of the parallelogram is your determinant. Okay, so in 3 dimension, what happens if you have a 3 cross 3 matrix? It's a parallelepiped, right? Then it's not the area, it's the volume, right? In n dimension also it generalizes. So in fact, if you start looking at what are the properties of the area of a parallelogram, and if you generalize that, you get that complicated formula for determinant. Okay, anyway, so what I'll try to or I attempt to do here is of course look at linear algebra again, but give some intuition along the way. Okay, so First of all, okay, so let's start with linear algebra. Okay, so first of all, what is the basic notion in linear algebra? This is about vectors, right? So let's start with 2-dimension. Let's observe a few things. Okay, so what is a vector space? You guys know? Huh? What is a vector space? I'm sure whoever taught you would have rigorously defined what a vector space is, right? So what is a vector space? Huh? No one? Come on, guys, you should, at least somebody should answer. So you are in 3rd year BTech IIT, so you should know what a vector space is. Huh? Not necessarily, right? So vector space need not be Euclidean. Come on, this is like you just take vector space and say set of all vectors. No, a space of all vectors. No. Okay, so you had a definition, right? So we say that set V is a vector space over R if blah 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 blah, right? So now, well, it's very hard to remember those, right? So how do you remember those? Well, instead of remembering, let's see what a vector is in 2-dimension, or the vector that you would have studied in your pre-university or high school, right? So you have 2 components, right? For example, X and Y, right? Do you agree? This is an example of a vector, right? So we call this as a vector. Now let's try to understand how this space behaves, right? It's all the 2 points x, y, x and y are numbers, right? So how does it behave? Now, what is the first thing that you can observe? So if you want to study this the vector space or the vectors, what are the kind of operations you do? The first thing you do is addition, right? I want to add 2 vectors. Maybe this is x dash, y dash. I want to add 2 vectors. What else I need to do with vectors? I want to shrink the vector or elongate or reverse, right? These are the operations, right? So I start with 2 things, right? So first is plus. I should tell how to add vectors. Very easy, right? How do you add these 2 vectors? Parallelogram, whatever you form the parallelogram, this is your addition. Actually, this point will be x plus x dash, y plus y dash, right? This is a very simple way of adding 2 vectors. This is how you define, right? This is how I'm going to add 2 vectors. Now, this plus is different from this plus, okay? So these are all subtle things that you should keep in mind. What is this plus? This is the usual addition of numbers. This plus that I'm going to talk about is the addition of 2 vectors. How do you define that? Through this, right? Is that fine? Okay, so basically x comma y plus x dash comma y dash is, I'll use x, maybe I'll use this plus x dash comma y. Okay, so I have to use y dash. So this is the definition of this plus. Okay, this is how we define. So you know how to add vectors. What else you need? Multiply. Of course, I cannot multiply 2 vectors. Doesn't make sense, right? It doesn't lead to anything interesting. So I want to, let's say, elongate or whatever, right? So how do you do that? You take a number alpha, right? Multiply by xy. Well, this multiplication is not the usual multiplication, okay? So it's a different multiplication. How do you define this? Alpha x, alpha y. Very easy, right? So it's like, you understand, right? Okay. Now with these 2 operations and numbers in mind, right? R, right? Because we did all the things. For example, it's a bunch of numbers and so on, right? So for example, how do I take a vector and make it, let's say, I can increase the length or decrease the length by multiplying it by a number. Okay, so what are the ambient space here? You have a bunch of vectors like x comma y, x belongs to R, y belongs to R. That's the vector space, right? And what are the 2 things you have? Of course, it's over R because I'm going to change the length using numbers. Okay. What else I need? I need a plus. How do I add vectors? With this, let's try to understand what are the properties, right? So if you take 2 vectors and add them, you know how to add. What do you get? Get another vector, right? Where does it lie? same space, right? So for example, I call this space or the vector space as R2. Okay, it is all the points. Well, it's a set, right? X, Y, such that X belongs to R, Y belongs to R. This is my space. This is a vector space. It's a two-dimensional, whatever. I haven't defined dimension, but this is your vector space, right? Now, what are the properties? The first thing that we observed is that if you take two vectors, let me call V belong to R2, implies you know how to add vectors, right? U plus V, which is same as V plus U. You can check that, right? Because the usual addition commute, so belongs to R2. What is this called? It's called closed under addition, right? Well, this is a very important property to have, because if you add two things, it goes out of space, and I mean, there's no point in adding, right? So you cannot, without thinking about anything, you cannot add. Okay, this is obvious, right? What else you have? Of course, there is a zero vector, right? What is this zero vector? 0, 0. Okay. Of course, you always have a zero vector. What is the third thing? You take any vector, there is an opposite vector. When you add them, you get 0, right? That is also another property, key property. So for every V in R2, there exists a U in R2 such that U plus V is V plus U is 0. Okay. What do you call this U? It's additive inverse of V, right? Minus V. That's what we call. Okay. What is the other thing that we have about vectors? You just come up with something, no? Some properties. Huh? Multiplying by? No, I can multiply a vector with a number. That I can do, right? So that means I can increase the length or decrease the length, reverse the length, and so on, right? So I'll still get another vector, right? For every alpha, let me write this, and maybe for every alpha and V in R2, alpha times V belongs to R2. I can always change the length without any problem. Anything else? Now I can take three vectors and I can add the way I want, right? It doesn't matter how you add. So for every U, V, W in R2, U plus V plus W is same as U plus V plus W. It doesn't matter how this associates. I mean, it doesn't matter, right? What else you have? I know it's boring, but we will write all the things at least once. Okay. So what else? Anything else that we can write? So for every U, V in R2, alpha in R, alpha times U plus V is alpha U plus alpha V. Okay. This is another. You agree? Anything else? Yes. Anything else? Did I forget anything? Okay. 7. Let me see if I have forgotten anything. So one more thing. So this is another boring stuff. So 6, 7. For every U in R2 and alpha, beta in R, alpha plus beta times U is alpha U plus beta U. It doesn't matter. So you can take a bigger number and multiply the vector, get a very large vector, or I can take the vector, multiply by a smaller number, multiply the same by some other smaller number, and add them, right? Doesn't matter. Okay. Okay. So now homework could be to check if I have missed anything. Okay. So probably if I had missed, I can write it, but it will be boring. So now what I can do is I can change this to R3. What will happen? Z. All that I have to do is this, right? Nothing changes. Okay. Still the same property. Okay. R for Rn general. Well, why to restrict to Rn, right? So I will replace this by a symbol. Okay, so what I'm going to do is I'm going to replace this by some V. Okay, so V, V, and V. Okay, right? So you take any set V, we call it as a vector space. Of course, you should always have this alpha, right, which is a number. So if we say that it's a vector space V over R if all these properties are satisfied, right? Now it need not be vector. For example, okay, so now since we are running out of time, so I'll just give a couple of examples, interesting examples. So you look at this vector space V, which is set of all A, B, C, D. What is this? Such that A, B, C, D belongs to R. What is this? This is the set of all 2 cross 2 matrices, right? How many of them are there? Yeah, uncountably many, right? Do you agree? So now, is this can I think of matrices as vectors? Yes. Why? You take 2 matrices. I know how to add them. So if I add 2 cross 2 matrices, I'll get another 2 cross 2 matrices, which is already there in alpha. I know how to multiply alpha with matrix, right? It's alpha A, alpha B, alpha C, alpha D. That will be 2 cross 2 matrix, right? That will be another 2 cross 2, so it's closed. So you can check that all the properties are satisfied. Do you agree? Right? There is nothing strange about this, right? Of course, you have 0, 0 matrix also. Okay, not a interesting one. Can somebody give me an interesting example of a vector space? Yes, anything? Okay, so let me use this thing, a0 plus a1x plus a2 x squared, such that a0, a1, a2 belongs to R. What is this? I'm collecting all possible second order polynomial in a basket, that is P, right? Now, do you think this forms a vector space? Yeah, you take two order second order polynomial, add them, you get another second order polynomial, right? For every second order polynomial, there is a negative second order polynomial. When you add them, you get 0 polynomial, which is 0 plus 0x plus 0x squared, right? Which is 0 basically, right? And then what else? It doesn't matter how you add 2 polynomials, it commutes, right? And it satisfies all the properties. Do you agree? So now, instead of studying vector space like R3, Rn, we can study a vector space V, right? So which has a very general property. So what abstraction does is, instead of writing a book for Rn, book for set of all polynomials, book for something else, you just write one book called linear algebra, right? So which deals with everything. Do you agree? Okay. So now one more example. This is another. This is set of all function from 0, 1 to 0, 1. Okay. Such that f of 0 equal to f of 1 equal to 0 and f is continuous. Okay. What kind of, you know what this is, right? So you have a function from 0, 1 to 0, 1. It is continuous. At 0, it should be 0, right? And 1, it should be 0. So that's such collection of functions. Do you think this is a vector space? Yes or no? Yes or no? Huh?
No.
Why do you say that it's not vector space? It's not.
Suppose we have some addition, which is like 0.7 plus 0.7. So
Okay.
it will go out of bounds.
Okay. Now I'll do this. Is it now? Can you say? Is this a good catch? Yeah. So now, do you think this is a vector space?
Yes.
Right? You know how to add 2 functions, right? The usual addition, right? To take 2 functions which satisfy this, if you add them, If you add to continuous function, it will be continuous. We have already seen that, right? We haven't proved, but that's an exercise. So it's closed under addition. For every f, there is a minus f also. Minus f is continuous. When you add them, you get 0, right? It doesn't matter how you add. F plus g is same as g plus f, right? Alpha plus beta times f is same as alpha times f plus alpha beta times f. So it satisfies all the properties. So this is also a vector space, right? Interestingly, vectors is not just, we started out with the usual vector that we can, we can see, and then generalize that, but that generalization included a lot other things, right? Therefore, if you understand, for example, this simple picture here, right? So this simple R2, you will also end up understanding a lot about various other weird things, right? You can say a lot about other things also. For example, Fourier series, right? So you can think of that as, those who have studied that, you can think of that also as some sort of each basis as your vectors and so on. We'll see that. Okay. So now in the next class, what I'm going to do is I'm going to generalize this, meaning I'm going to write a proper definition for a vector space, and then we will see other things like linear independence and few other things that we need for us to look at other aspects of data analysis or mathematics for data analysis. Okay, this will be a few classes. I mean, it's longer than calculus, but very important. Okay, if you have any questions, feel free to ask. Even if you have questions about applied things like pure engineering, or if you want to understand certain things more clearly, feel free to ask questions. Okay, I'll stop here. Yeah, so we'll meet next week. So any questions? Okay, those who are online, if you have any questions, you can ask after 5 minutes. Okay, so I'll sign.